Hello, my people. I hope we're doing well today. As discussed in class, we are now going the other way. So we were finding the derivative of functions and applying that derivative to certain circumstances, and starting with Chapter 5, or actually more specifically starting with the very last section of Chapter 4, we're going to be going the other way. Anti-differentiation is sort of a lead-in to our discussion of integration. Now, when we are doing anti-differentiation, or later when we're doing integration, what we need to remember is that it's a little more complicated because we have to basically have an identifiable derivative in order to undo it into its original function. So there are actually some anti-differentiation and integration problems that can't be done. So we're going to concentrate on looking at those expressions that we're being asked to anti-differentiate or integrate, and we're going to be asking ourselves the question: what is this expression or function the derivative of? Okay, and it has more than one answer. So like we did in class, we're going to consider f of x is equal to 2x. Okay. Now, if we were doing differentiation of x squared, we would recognize the fact that 2x is the derivative of x squared. But then we remember that constants, because constants have a derivative of 0, 2x is the derivative of x squared plus 1, x squared plus 2, x squared plus 3, and on and on and on and on and on. So 2x is not the derivative of a function, but really a family of functions related to each other by a non-specified or a non-specific vertical shift. Okay. Therefore, when we anti-differentiate, we need to basically put something there to represent that sort of random constant that could, or most likely is there. We just simply don't know what it is, right? And so we basically, instead of doing big F of x, and of course, just as a way of reminder, big F of x is the way we instead of, when we go from f of x to the derivative, we put a hash mark and it's f prime, right? When we anti-differentiate, we go from lowercase to capitalization. So big F of x is equal to x squared plus c, where c can be, 1, 2, 3, or any one of the constants, any constant, basically. It's annoying to have to do this. It'll be the thing that you are constantly forgetting to do, and I'll constantly be saying plus c, plus c, plus c, plus c. It'll be the thing that you forget on this first test, but after a while it just becomes second nature. Okay, so the anti-differentiation formulas are about what you would expect. They're just undoing the derivative formulas, right? So basically, when we have this one up here, as we discussed in class, x to the n, if we were actually taking the derivative, right, we would do f prime of x is equal to n x to the n minus 1. But since we're actually going the other way, we're actually going to add 1 and then divide by that new exponent, okay? And that should make sense to us because that basically creates something like this, where 1 over n plus 1 is our coefficient, right, of x to the n plus 1. And if I were to then differentiate that, by the way, there's a plus c right here, it would become f of x is equal to n plus 1 over n plus 1 x to the n. And of course, that just gives us x to the n. So if you ever want to check your work, it's really, really easy. Have I anti-differentiated correctly? Well, differentiate, and if you get back to the original, then you've done it correctly. All right. On this sheet, this is basically a little chart that I stole, basically, and it basically reveals the majority of the anti-differentiation formulas that we're working for. We, however, have not done hyperbolic, so what I want you to do is I want you to ignore this line right here. Okay, we have not done hyperbolic trig, just because, it's not all that difficult, and you don't run into it all that often, and so it's just one of those unnecessary things, kind of like unnecessary formulas, one of those things that I just didn't think was worth it. But the rest of these, e to the x, it is the derivative of e to the x. Cosine is the derivative of sine. Secant squared is the derivative of tangent. 1 over 1 plus x squared is the derivative of arctan. And on and on and on and on and on. But you'll notice that arc sine is here, but arc cosine isn't. And if you remember what the derivative of arc cosine is, it's just the negative, right? Well, when I anti-differentiate or differentiate, the coefficient comes along for the ride. So you can actually just treat that negative as the coefficient coming along for the ride, and you don't have to anti-differentiate or integrate into arc cosine. It just becomes negative arc sine. Okay. So all of these should look familiar. We are used to going from here to here, and now we're just going the other way. Well, that's all well and good. Let's do some examples. Alrighty, now f of x is equal to x to the 5/2 plus 2. Well, remember that we add 1 to the exponent and then divide by the new exponent when we're undoing the power rule. So big F of x is going to be x to the 7/2 over 7/2. But to divide by 7/2 is to multiply by 2/7. Now, if 2 is the derivative of something, 2 is the derivative of what? Well, 2 is the derivative of 2x, and then we just have to tack on a plus c after that, and we're good to go. Now, this one right here, you should recognize the fact that you're like, oh yeah, I remember something about that. Remember that when you had, let's say you had y is equal to the square root of x, which was x to the 1/2, and dy dx wound up being 1/2 x to the negative 1/2, or 1 over 2 root x. So that's close to being this right here, right? But let's just go ahead and do it by the formulas that we've actually looked at. I need to, of course, change this into f to the negative 1/2, x to the negative 1/2. And when I anti-differentiate it, remember I add 1, and then I divide by the new, and to divide by 1/2 is to multiply by 2, and I get that, which makes sense because that 2 is there. Because this was not exactly what this derivative was. It was lacking that 2 in the denominator right there. Now, this one right here, we have a trig one. Okay, and we're going to try to get through a couple of examples of a little bit of everything so that we have a nice smattering of example problems. Now, sine, remember the 2 just comes along for the ride. Sine is the recognizable derivative of negative cosine. And cosine is the recognizable derivative of sine. So this just becomes negative 2 cosine x minus sine x plus c, right? And notice that sometimes even I'm concentrating on the antiderivative and at least getting the plus c just a little bit late, okay? Let's move on to the next one. Alrighty, well, again, remember that what we're dealing with right here is something that has is a rational expression that has a monomial denominator. Well, just like differentiation, anti-differentiation, we're going to try and put it into a form that's going to be easiest to deal with. In its rational structure, it's not that easy to deal with. But if I pull it apart, separate the fractions, and reduce both of them, I'm going to get 4x to the 1/2, okay, with this first term over x, and then minus 1 over x is minus x to the negative 1, okay? Now, it's probably better to not put that as a negative exponent, just to put it as that, because as that is recognizable as the derivative of natural log. So remember, big F of x, this is going to be power rule, and so I add 1, right? And I get x to the 3/2 over 3/2, and then I have natural log, and remember to put the absolute value around the x, because like we talked about in class, the whole purpose of that is because 1 over x has a domain of negative infinity to 0 and 0 to infinity. The domain of natural log x without the absolute value bars is only 0 to infinity. But in order for that antiderivative to be able to describe and help us analyze the entire original graph over its entire domain, what needs to happen is we need to put the absolute value bars there such that it can entertain the negative values in the domain of the original function. You get natural log of absolute value of x plus c, and that right there is our antiderivative. Okay. Now, we have here e to the negative x. Well, remember that when we took the derivative of e to the negative x, it became negative e to the negative x. So, I mean, you could actually change this into negative e to the negative x so that it actually does look like it, but you know, I mean, this is a really easy, I mean, this is officially chain ruled, but it's so easy that you kind of forget that that's chain rule, right? Because the inside is merely just a negative sign. But if you need to actually do this in order to see it, in order to see each term as a recognizable derivative, then do so, right? And so big F of x winds up being, well, this is obviously the derivative of e to the negative x. This is the negative that comes along for the ride. This whole thing becomes e to the negative x. And of course, secant squared is the recognizable derivative of tangent. And then we just have to tack on our plus c, and we're good to go. Alrighty. This one is going to be just a little bit more difficult because you're looking at this and you're going, that looks vaguely familiar. Hopefully some of you recognize it, but if I pull the 10 out, you should all recognize it. That right there, inside the parentheses, is the recognizable derivative of arcsine. So, and the 10 in the numerator can be pulled out in front so that it sort of looks more like the coefficient that it is. And x becomes 1/2 x squared. You know, x squared over 2, but you can pull the divided by 2 out as a 1/2 coefficient. I kind of like it better that way. It's a little tidier. And this one becomes 10 arcsine x plus c. Alrighty. Now, let's go ahead, and that plus c should be kind of bugging us a little bit because you're like, well, what use is that? Well, you can actually be given a problem that has an initial condition, and we did a couple of these in class, where that random constant becomes a particular constant, right? Because basically, if you have a graph and you have a point, here, let's go ahead and look at it this way. Some of y'all are more visual, so let me go ahead and do this. Okay. Let's say that, you know, we have our antiderivative, and our antiderivative is one of these, right? They're all the same curve. They're just, you know, moved up by c or moved down by c. If you then basically specify a particular point that goes through, then it's not any one of these. It's necessarily this one, right? This becomes the actual antiderivative with a particular constant, whereas without the initial condition, it could have been any one of these, right? It could have been, you know, -5, -3, +1/2, +7, or whatever. But in this case, this particular point, as we sort of think about the graph, the family of curves sliding up and down, basically at one point, that one point sort of locks it in and it becomes a particular constant. So let's go ahead and look at a couple of examples of those. This one is sort of laid out for us from the get-go. Let's say we have f prime of x is equal to 1 over x cubed, or x to the -3, and the initial condition gives us the ordered pair of 1, 1. Remember that this is basically function notation for goes through the point 1, 1. Okay? Now we need to find the antiderivative. And of course, we're going to do that by the power rule. I'm going to add 1 to -3, and I'm going to get -2, and then I'm going to divide by that new exponent, and then I'm going to add c to it. Well, I'm going to go ahead and simplify that, and that becomes -1 over 2x squared plus c. That makes it a little cleaner. Now what I'm going to do is I'm going to take this ordered pair, and the f of x becomes 1, the x becomes 1, and now I'm solving for c. This becomes 1 is equal to negative 1/2, so c is equal to 3/2 if under this particular, under those particular circumstances. So our function then becomes f of x is equal to negative 1 over 2x squared plus 3/2, and that locks it into being a particular curve rather than merely a family of curves. All right, let's do some more examples. Alrighty. We have f prime is equal to x cubed minus 8x squared plus 16x plus x. Let's go ahead and take the antiderivative. I get x to the fourth over 4, or 1/4 x to the fourth. I get 8 times x cubed over 3, or 8/3 x cubed. I get 16 times x squared over 2, or 8x squared. And then I get x plus c. Well, this right here is an initial condition, makes things very, very easy. If basically it goes to the origin, if the y-intercept is 0, then obviously c is 0, if it's a polynomial like this. Because basically when you plug in 0 for all of the x's, all of those terms go to 0, and the only thing left to equal this 0 on the other side is the c. So basically this one goes bye-bye, 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 and c is equal to 0. So my actual function under these conditions is the original with a c value of 0. Right, and notice when you're given a problem with an initial condition, you're no longer going from f to big F. You're going from f prime back to the original function, your original f. But it's the same move, okay? Now, because if f prime is the derivative of f, then f is the antiderivative of f prime. Should make sense. Now let's go ahead and look at this f prime right here. Now let's go ahead and look at that first term. That first term, cosine, is the recognizable derivative of sine, right? And that second one is the recognizable derivative of tangent. And then I need plus c. Well, this looks kind of nasty, but it shouldn't really be that big of a deal, because you notice that when you take sine or cosine of pi over 4, that's where you're going to get that root 2 over 2. So let's go ahead and plug it in. And we get 2 plus root 2 over 2 for my f of x. And then everywhere where I have an x, I need to put a pi over 4. So sine pi over 4 plus tangent pi over 4 plus c. Well, sine of pi over 4 is going to be root 2 over 2. Tangent of pi over 4 is going to be 1. And so c is equal to 1 after you get rid of all that, right? That you can subtract that from both sides. And when you subtract 1 from both sides, you get c is equal to 1. That means that with this initial condition, we have f of x is equal to sine x plus tangent x plus 1. And that is our antiderivative. Alrighty, I have a little bit more. I think I'll probably just keep going and make it a single video rather than two. That doesn't seem to be a really good place to stop the video. Alright, so we solve the initial value problems. F double prime. Okay, so we need to get back to f of x, but notice that we have two conditions right here, so that's kind of nice. Let's first of all find what our f prime is. Now that's going to be, the 8 is going to come along for the ride, and the x cubed is going to be x to the 4th over 4, so that winds up being 2x to the 4th, right? Because 8 over 4 is going to reduce to 2, plus 5x plus c. Now this is f prime, so I'm going to use this right here, this first initial condition, to actually find that value of c. And what happens here is, let's go ahead and just plug in the 8. 8 is equal to 2 times 1 to the 4th plus 5 times 1 plus c. This is 2 plus 5 or 7, so c is equal to 1, and therefore f prime is going to be equal to 2x to the 4th plus 5x plus 1. When I anti-differentiate that, I'm going to get 2/5 x to the 5th this is going to become 5/2 x squared, because in this one the 2 comes along for the ride and I get x to the 5th over 5, and then if you just sort of use the commutative property to take the 5 out from underneath x to the 5th and combine it with the 2, you get 2/5. Same sort of thing happens here. This is 5 times x squared over 2. So let's put the 2 underneath the 5 instead of the x squared, and I get 5/2 x squared plus x plus, now here's the thing. You have c. It's not the same c. If you want to distinguish between the two, you can call this c sub 1 and you can call this c sub 2. You can call the first one c and the next one capital D. It really doesn't matter. Now this one right here, we're going to go ahead and plug in 1, and it's going to be equal to 0. 0 is equal to 2/5 plus 5/2 plus 1 plus c2. Well, 2/5 and 5/2, I mean, you can get a common denominator, obviously. That's going to be 4/10 plus 25/10 plus 10/10 plus c2 is equal to 0. That's 39/10, so c2 is equal to negative 39/10, which is ugly but doable, right? And that means that with those two initial conditions, what I actually have as an original function is that. Okay. Alrighty, let's go ahead and do this next one. Now this next one is a little bit different because I do have f double prime, and I do need to get back to my original f, but I don't have an f prime initial condition and an f double prime. So I may have to differentiate, I may have to anti-differentiate twice and then set up a system of equations. Let's go ahead and see. Now I know that f prime is going to be equal to 2 times the whatever e to the t is the recognizable derivative of, and that just winds up being e to the t, plus 3, and sine is the recognizable derivative of negative cosine. So let's actually turn this into minus 3 cosine t plus c1. All right, it's annoying, but we're going to have to go ahead and anti-differentiate again. This first one remains the same again. It's still 2e to the t. Cosine, however, is the recognizable derivative of sine, so it becomes minus 3 sine t. This becomes c1t, and we get a second constant, c2. Okay. Well, we have two initial conditions. Let's go ahead and plug in the first one right here, okay? And so we get 0 is equal to 2e to the 0 minus 3 sine of 0 plus c1 times 0 plus c2. Well, this winds up being really, really nice because that goes bye-bye, that goes bye-bye, and you know that your c2 is simply going to be equal to the negative of that, which is, of course, 2, because e to the 0 is 1. So if your c2 is equal to negative 2, then you know right off the bat that, and you can go ahead and plug it in because you do know it, right? Minus 2. And now I'm only looking for c1. It was really fortuitous that my first initial condition, I didn't have a c1 and a c2. You remember that when you were solving for systems of equations, every once in a while, it would be a really easy problem because one of the variables would fall out and you would be able to solve for one right off the bat. This is that kind of situation. Now that I have c2, I can go ahead and just concentrate on solving for c1, and I'm going to use this other initial condition right here. I have 0, 2e to the pi, that's going to be a little bit nasty, 3 sine of pi plus c1 pi minus 2. Well, this is a z problem, right? You're solving for c1 right there. And so pi c1, shove everything over to the other side, except for this one because that's 0, right? And you get 2 minus 2e to the pi, and c1 is equal to 2 minus 2e to the pi over pi. Ugly, yes. Doable, certainly. So 2e to the t minus 3 sine t plus 2 minus 2e to the pi over pi t minus 2. And that is an ugly coefficient for that linear term right there, but it is what it is. Okay. Let's go ahead and move on to the ones that are a little more specific. I did this for you in class where I reminded you of that formula that you've been dealing with in physics. It's basically the position of something that is either dropped or thrown with respect to its height based upon what we know about the acceleration due to gravity on Earth. And you know that acceleration, we just use the letter g. I mean, in class, we went ahead and were specific, and we used the value for feet per second, which is -32. Obviously, meters is going to be different because it's -9.8. But here we'll just do it in general, and we'll talk about it as g. Now, when we take the antiderivative of a of t is equal to g, we're going to get v of t is equal to gt plus c. But remember, that c is a very specific c, because if I plug in 0 for t, v of 0, I'm going to get rid of this first term, v of 0 is equal to c. So that means the initial velocity is that c value right there. And we have a special way of, representing that with notation, which is v naught. So instead of gt plus c, we're going to get gt plus v naught. Okay, we're just renaming the c. And then we anti-differentiate again. That t becomes t squared over 2. That v naught becomes v naught t, and we have another constant. Now again, if you wanted to show the difference between this c and that c, you could provide subscript, or you could use a capital D down here. It doesn't really matter. But again, this is a very specific c value, a very specific constant. If we plug in 0, s of 0 is initial position, and it's equal to c. So s naught winds up replacing this c, and we get 1/2 gt squared plus v naught t plus s naught. And of course, the negativeness of the acceleration due to gravity is contained within the g right there. So let's go ahead and let's do an example. Okay. We find the initial formula, position formula by anti-differentiation, and confirm by formula. Okay. Well, if this is a of t, and it, you can call it it's a constant, but it is a function. It's a constant function, right? So if a of t is this, then basically v of t, being a of t's antiderivative, is -32t plus. And let's go ahead and just not call it c. We'll call it v naught, because we know what it is based upon our discussion from the previous page. Now, this v naught right here is 128 feet per second. So we'll go ahead and say v of t is equal to -32t plus 128. Then we need to go ahead and anti-differentiate again. And of course, velocity's antiderivative is position. That's s of t, and we get -32 over t squared over 2 plus 128t plus, and of course we get another c, but that's a very particular c. We know what it is, and that's s naught. And of course, s naught here is going to be 0, so s of t is equal to -16t squared plus 128t, and that, of course, is it by anti-differentiation. We could, of course, have just done -1/2, or sorry, the negativeness is inside, 1/2 gt squared plus v naught t plus s naught, and then just plugged in, right? But just like the quadratic formula only exists because of completing the square, this formula only exists because of this anti-differentiation practice. So now, when we're talking about position and velocity and acceleration, it doesn't always have to be a falling object, right? It can be a different scenario apart from gravity, and therefore we're going to do kind of the same thing, but we're going to do it with a acceleration function rather than acceleration constant. Yay, us. All right, so if this is a of t, then we know v of t is going to be 3 sine t plus 2 cosine t plus, and of course this is just going to be v naught, right? Because the antiderivative, or cosine, is the recognizable derivative of sine. Negative sine is just ignoring the 2 right here. Negative sign is the recognizable derivative of cosine. Of course, V naught is going to be equal to 4. And we could actually do the, plugging it in, but it's just sitting right there. So we'll just go over and grab it and call it 4. And then position is going to be, sine is the recognizable derivative of negative cosine, right? And cosine is the recognizable derivative of sine. 4 is the recognizable derivative of 4t. And then, of course, we have initial position. Well, initial position is 0. That's really nice. So I don't like negative leading coefficients when I can help it, so I'm going to go ahead and flip those first 2 terms around, and that winds up being my position function based upon the two stages of antidifferentiation. Okay. That for this video. If you have any questions, please do shoot me an email. Bye.